Hello everyone, this is our third video lecture. Let's continue with seeing further examples regarding the use of pumping lemma to show that a given language L is not regular. Our next example language, let's consider the following. W in, again, 0, 1 star. W is a string of zeros and ones, such that W is equal to W1, let's use a new notation for this, R. So basically W consists of two substrings. The first half is W1 and the second half is W1R, where W1R, this new type of a string, is formed by reversing every bit in W1, by reversing every bit in W1. Just to give an example, for instance, 0, 1, 1, if this is the W1 part of our string, to get the second part, W1R, we need to take the same string and reverse every bit. First bit should be 1, second bit should be 0, third bit should be 0. This is W1R. So such a string is inside this language, just to make it clear what we mean by this language description. Now, we will show that this language is also not regular let's first try to examine the language, examine the possible strings in the language, trying to guess, trying to actually convince ourselves that the language is not regular. How? In order to recognize strings of this sort, if we are given an input string, it seems that somehow it is necessary to record the first half of the string somewhere, such that we can check whether the second half is actually the reversed version of the first half. Okay. This tells us that in order to do this, in order to record the first half of the string, we actually might need indefinite amount of storage, indefinite amount of memory, or indefinite amount of states for a supposedly existing finite automata to recognize such a language, because the length of W can be anything arbitrary. So altogether, this actually kind of hints that this language L should be not regular. In order to formally prove that our guess is true, we will use pumping lemma. Again, as usual, we will start by picking a special string S. Let's pick our special string S to be 0 to the P, 1 to the P. Note that in the last couple of examples, we have been choosing the same string to work with our pumping lemma. To be able to use pumping lemma on the special string S, remember we had two conditions: that the string S should be in the language. Let's check if this is true. The string S, if we divide it into two halves, the first half consists of P many zeros, and the second half consists of P many ones. So it's in the format W1, which is this part, and the reversed bit version of W1, W1R, which is this part. All the bits in W are reversed in here. So the string belongs to the language. And the second condition was that the length of the string should be greater than or equal to P, which is true because length of the string is 2P. Now, continuing with the usage of our pumping lemma, for any partition of the string S into 3 XYZ, assuming that the conditions 2 and 3 of the pumping lemma hold, that is, assuming condition 2 says length of y is greater than 0, condition 3 says length of xy together is less than or equal to p. Assuming these two conditions hold, we need to show for some I, there exists I such that x, y to the I, z, repeating y, I many times, is not in the language. If we can do this, then we are done. This shows that the language L is not regular. Let's again try to visualize the string S divided into 3 x, y, z. We have a bunch of zeros, p many zeros, followed by p many ones. So the length in here is p, the length in here is p. This is our string x, y, z. Again, let's concentrate on the middle string y. Where can the middle string y be in this whole string? Due to this third condition of our pumping lemma, length of xy being less than or equal to p, y must belong to this initial part of the string consisting of zeros. Y belongs here, which means that y cannot be here, y cannot be here. Why? Because the length of x and y together is less than or equal to p. X and y together should be somewhere among the initial zeros. And secondly, the second condition of the pumping lemma says length of y should be greater than 0, which means that y is somewhere here and it's not epsilon. It consists of some positive number of zeros. To show that, we can find some special value of I such that xy to the I, z. This time, different from the other examples, let's pick I being equal to 0 rather than in the other examples we have been fixing I to be 2. Let's consider this new substring x, y to the 0, z. Okay, how does this new string look like? It again contains a bunch of zeros followed by a bunch of ones. How many zeros should we have in this string? Since y in the original string belonged among the zeros and it consisted of a positive number of zeros, in the new substring we are removing y. This tells us that the length of the number of zeros in the first part of the string should be less than p, because originally we had p and we remove y from the original string. Since there has been no modification on the remaining part of the string, the number of ones is still p. Now let's see whether this new string consisting of less than p zeros at the beginning and exactly p ones at the end still belongs to our language L or not. To verify this, remember that for a string to belong to the language L, we should be able to divide it into two equal halves such that the second half is the first half's reversed bit version. Now, in this new string, where should the middle line of the string belong to? So we can see that we have less than p zeros, we have p ones in here. This implies that the middle of this new string, should lie along the ones that we have. So if we draw this line, the length in here is equal to the length in here, should be equal to the length in here. Okay, this implies that if we take this first half to be W1, it's easy to see that the second half is not equal to W1's reversed bit version. right? Because in the first half of the string, we have zeros followed by a positive number of ones, whereas the second half of the string consists only of ones. If it were to be the reverse version of the first half, it had to contain some zeros in here, but that's not the case. Therefore, this new string x y to the power z is not inside our language L, which by pumping lemma implies that language L is not regular. This example shows us that we can use any value of I in our proof using the pumping lemma. In this case, we have used I being equal to 0 to construct our new string of xy to the iz, and still we are able to show that xy to the iz is not in the language L for a specific I where I is 0. Therefore, this proves us that the language L is not regular. Let's do yet another example. L is W in 0, 1 star. This time let's do a similar example to the previous one. W is equal to W1, W1. This time, rather than in the previous example, it was W1 and W1R. Okay. So basically this tells us that if you split a given string into two equal halves, the first half corresponding to a substring should exactly be the same as the second half of our string. So for instance, 0, 1, 1, 1, 0, let's say this is the first half, followed by again 0, 1, 1, 1, 0 is in this language because it can be split into two halves such that the first half is the same as the second half. Thinking of this language, let's first try to see whether we guess this language to be regular or not. Again, as was the case with the previous example, it should kind of be clear that in order to recognize strings of this form, we somehow again need indefinite amount of storage because we need to somehow store the first half of the string so that we can check whether the second half of the string is exactly the same as the first half. But this points to something. It points to the fact that for doing so, we may need indefinite amount of storage or indefinite number of states in a supposedly existing finite state machine for this language. Okay, all this summarizes, or all this actually hints us the fact that L might be non-regular. To formally prove that L is not regular, again we will use pumping lemma. We start by picking a special string S. In the previous examples, most of the previous examples, we picked 0 to the P, 1 to the P to be our special string S. But in this example, we cannot simply pick 0 to the P, 1 to the P, because this string does not belong to the language. It should be the case that the first half of the string should be the same as the second half of the string. Okay. So what can we do? What special string can we pick? In this case, we will use a slightly different version of such a special string. We will use 0 to the P followed by a single 1 followed by 0 to the P and then again a single 1. Note that again we should kind of see that such a string should actually be useful in our pumping lemma, because it seems that to recognize strings of this form, we again need indefinite amount of storage or indefinite amount of counting. Let's see if the conditions on S are satisfied for the use of pumping lemma. The string is inside the language because the first half is the same as the second half, and the length of the string is greater than or equal to p, since its length is actually 2p plus 2. So we can use this string S in our in our non-regularity proof of this L using pumping lemma. For any partition of the string S into 3 pieces, x, y, z, again we should assume that conditions 2 and 3 of the pumping lemma hold. Assuming condition 2 says the middle part y should have length greater than 0, and condition 3 says the first two parts together, length of x and y, should be less than or equal to p. Assuming these two conditions are true, show the third condition is false. In other words, show there exists an I, so find a setting of I such that x, y to the I, z, repeating the middle part I many times, and we're getting a new string. That new string doesn't belong to the language. Let's try to again visualize this string S subdivided into 3 substrings x, y, z. A bunch of zeros, namely p zeros, followed by exactly 1, 1, followed by a bunch of zeros, exactly p zeros, followed by a single 1. This is what our string S or our string xyz looks like. Looking at this string, where does this middle substring y can be located in here? Due to this condition that length of x and y together, basically the two initial substrings, their length should be less than or equal to p. This means that xy starts here and xy can span only this range in here. Okay, so y, any part of I will not go this far, which means that y is somewhere among the initial zeros. Y belongs here, and we know that by this condition length of y is greater than 0, which means y is not epsilon, and y is not epsilon. In other words, it contains some number of zeros in this range. We can pick a special I as long as we show that x, y to the I, z is not in the language L. For this example, let's pick again I to be equal to 2. For I equal to 2, we have x, y squared, z. Let's try to visualize this new string, how it looks like. We will have a bunch of zeros. Now, we shouldn't be able to see that, followed by a 1. The number of zeros in here must now be greater than p, because in the original string y was among the zeros in here in the first part of the string, and we know that it contains a positive number of zeros, so repeating y once more should increase the number of initial zeros. For the rest of the string, it should be the same as the original string because there has been no change in that part. Zeros, basically p zeros in here, and a single 1. Okay. Now, considering this new string xy squared z, let's try to locate where the middle of this string should be. Okay, since we have increased the number of zeros, or in the original string, this was the middle of the string. But in the new string, we have increased the number of initial zeros, which means that this middle indicator, this line indicating the middle point, should slide to the left. So the middle pointer can be here, and so on. This is the middle of the new string. Okay? Since the middle of the new string starts exactly at this location, the first half of our string consists only of zeros, whereas the second half consists of the remaining substring. Okay? Therefore, if we take this first half to be W1, which only consists of zeros, it's easy to see that the second half of the string is definitely not equal to W1. The second half does not consist only of zeros, which implies that our new string is not in this form. Therefore, xy squared z is not inside our language L, which implies that language L is not regular. Let us consider yet another example. This example will be slightly different from the others because in this example we will see that we won't be able to apply the pumping lemma directly. So let's start with the example. Language L consists of the strings 0 to the n, 1 to the m, such that n is not equal to m. Okay? Basically, this tells us that the strings that belong to L should consist of a bunch of zeros at the beginning, followed by a bunch of ones at the end, and the number of zeros at the beginning is not the same as the number of ones at the end. Okay, so for instance, having 2 zeros followed by, let's say, 4 ones, this string belongs to the language L because it is in this format, zeros followed by ones, and the number of zeros is not the same as the number of ones. Okay. Again, let's try to first of all see how we construct a guess whether this language is regular or not. It seems again that recognizing strings of this sort may require indefinite amount of counting. Why? Because we need to somehow record the count or the number of zeros appearing at the beginning just to be able to check that the number of ones is not the same at the end. Okay? But such a counting might be indefinite because n and m are any arbitrary numbers. Okay? So, recognizing the language seems to require some indefinite amount of counting, which further implies that recognizing L requires an indefinite number of states in a supposedly existing machine for the recognition of L. And we cannot do so in finite state machines. Therefore, this hints us that the language L can be non-regular. Note that formally we use again pumping lemma to prove such a statement that language L is not regular. Let's try if we can do so. Our first trial. As usual, with the pumping lemma, we need to first pick a special string S that belongs to the language and that has length greater than or equal to P. For this, we pick, let's say, S to be 0 to the P let's say 1 to the p plus 1. Are the conditions of the lemma satisfied regarding the string s? The string s is inside the language because it's in the format zeros followed by ones, and number of zeros is not equal to number of ones. So it is in the language and its length is greater than or equal to p, since its actual length is 2p plus 1. So we can use this string s in our pumping lemma. What happens with the rest of our proof? For all possible partitions of the string s into 3 substrings x, y, z, assuming conditions 2 and 3 of the lemma hold, that is, assuming length of y is greater than 0 and length of x and y, the initial 2 substrings, together is less than or equal to p, making these 2 assumptions, if we can show that for some integer I, x, y to the I, z, basically repeating the middle substring y, I many times, the new substring doesn't belong to the language, then we would be done with our proof. This would show us that the language L is not regular. Let's try to see if we can do this. Let's visualize the string s partitioned into 3 x, y, z. We have a bunch of zeros followed by a bunch of ones. The number of zeros in here is p, because s starts with 0 p's, and followed by p plus 1 ones, because s is followed, the zeros are in s are followed by p plus 1 many ones. In this string, let's try to locate where the middle substring y can be. Since our condition 3 says length of xy together should be less than or equal to p, so xy is the first 2 substrings in our xyz, so they should start here. xy together should start here, and since their combined length is less than or equal to p, they can span, xy together can be spanning until here. Okay, they cannot, xy together cannot extend into the parts where we have ones. Okay, xy can be anywhere in this range, which means that y is anywhere in this range, somewhere here. Y is in this range. Note that y can contain this last 0, but it cannot extend further. Okay? Y is in this range of the initial zeros, and by the condition 2, y is not epsilon, which means that it is in this range somewhere here, and it contains some number of, a positive number of zeros. Okay, given this, and y is not equal to epsilon, it contains some number of zeros. Given this, can we find a special value of I such that xy to the iz is not in the language? Remember that for this part, it is enough to show that xy to the iz is not in the language, even just for one setting of I. But can we do this for any setting of I? Let's try, for instance, I being equal to 2. For I equals to 2, let's try to visualize xy square z. So xy to the iz becomes xy square z for I equals 2. What does it look like? We will have a bunch of zeros followed by a bunch of ones. Okay? Now, since y did not extend to the part where we have ones, in the new string xy square z, the number of ones did not change. It is still p plus 1. How about the number of zeros? What can we say about the number of zeros in here? So, the number of zeros in the first part of the string, originally it was p, but we know that y belongs to among the zeros and it's not epsilon, it contains a positive number of zeros, which means that in the new string this is greater than p. So it could be equal to p plus 1, it could be equal to p plus 2, and so on. Okay? But can we for sure say that this new string xy squared z is not in the language? Can we claim this? Because if we can claim this xy squared z is definitely not in the language, then we would be done with our proof that L would be non-regular. However, in this case, we cannot definitely claim this, right? Because it could be the case that the only thing that we know about y is that y is not epsilon and it belongs to this range of zeros, okay? Y, for instance, could be, for instance, 0, 0, 0, okay? And in this new string xy squared z, then, the new length would be p plus 3, the new length of the zeros, okay? Followed by exactly p plus 1 once. In which case, the number of zeros in the initial part would still be different from the number of ones in the second part, which would imply that the new string xy squared z still belongs to the language L. Okay? So this tells us that for any partition, considering any partition, we cannot find an I that works. We cannot find an I such that xy to the iz is not in the language considering any possible partition. Because considering y having 3 zeros, we can exactly see that number of zeros in the new string is not equal to the number of ones, so the new string still belongs to the language. Can we claim this? No. So, directly applying pumping lemma in this case, for this example, did not work. If the pumping lemma doesn't work for some language, does this imply that the language is regular? No. It just means that we couldn't use pumping lemma to prove its non-regularity. But there may be another way, an indirect way, of proving the same thing, that the language L is not regular. That's what we will do for this example. So, rather than considering the language L and trying to directly apply pumping lemma on L, we will try to consider a related language to this language L and try to see whether we can apply pumping lemma on that new related language. How do we construct a related language to this? This one says 0 to the n, 1 to the m such that n is not equal to m. One related language that we have seen that we can easily apply pumping lemma is the following. Let's call this L prime. Consider the following related language, L prime. 0 to the n, 1 to the n. This one enforces the fact that zeros are followed by ones and the number of zeros is exactly the same as the number of ones. Let's consider our original language L, 0 to the n, 1 to the m, such that n is not equal to m. This was our original language L. Remember that we are trying to prove this language is not regular, but we couldn't do it using directly the pumping lemma. Let's rather now concentrate on this related language L prime. Let's try to see what the exact relationship between L prime and L is. L prime is actually equal to L complement intersected with 0 star 1 star. Why? If we consider L complement, it should first of all includes all strings of zeros and ones not in this format. Basically, the order of zeros and ones are not in this order. Or it contains strings that are in that format, but number of zeros is equal to the number of ones. Okay? So to be able to eliminate the first case of strings, we intersect our complement with 0 star 1 star. Okay? Intersecting the complement with 0 star 1 star tells us that we should have strings in this format, zeros followed by ones, and since we are taking the complement, the strings in that format should also have equal number of zeros and ones, because we are considering the complement of this. Okay? Now that we have the exact relationship between these two languages, L prime and L, what can we do? It should be enough to see that if we prove that this new language L prime is not regular, then that also implies that this original language L is also not regular. Why? Because consider the following. If it were otherwise, if L were to be regular, then L complement would be regular, because remember we have seen the fact that regular languages are closed under the complement operation. So if L were regular, this would be regular. Since this is already expressed as a regular expression, this language in here is also regular. And finally, we have seen that the regular languages are also closed under the intersection operation, implying that the intersection of two regular languages is also regular, which would imply us that the intersection of these two would also be regular, and L prime would have to be regular. So if L were regular, L prime would have to be regular. But if we prove that L prime is non-regular, then L has to be also non-regular. Okay? Otherwise, a contradiction arises. So let's concentrate on proving L prime being non-regular. How would we prove L prime is non-regular? Again, we can use pumping lemma. Pick a special string S. In this case, let's pick 0 to the P, 1 to the P. Our string S belongs to the language and its length is greater than or equal to P. So we can apply pumping lemma using this string S. For all possible partitions of the string S into 3 XYZ, assuming conditions 2 and 3 hold, basically assuming length of y is greater than 0 and assuming length of x and y together is less than or equal to p, if we can show that there exists some setting of I such that x, y to the I, z is not in the language, then we would be done. We will have proven that this language L prime is not regular. Let's try to visualize S partitioned into these three substrings x, y, z. Zeros followed by ones. We have p zeros followed by p ones. Now in this string x, y, z, where can we locate the middle string y? Third condition tells us that the first two substrings x, y, they start here and they can span all the way up to here. x, y together cannot exceed further because their length together is less than or equal to p. We have p zeros in here. So y is somewhere here. Y belongs to this range. And by the second condition, we know that y is not epsilon, which means it contains some number of zeros. Now, can we find a setting of I such that xy to the iz is not in the language? It's easy. Let's pick I equals to 2, x, y squared z. Consider x, y squared z. How does it look like? We have zeros followed by ones. How many zeros and how many ones do we have? Since y belonged to the zeros in the initial part, and in the new string we repeat y twice, number of zeros in here is greater than p. And since there was no modification on the second part, number of ones is p. This implies that this new string xy squared z consists of more than p zeros at the beginning and exactly p ones at the end, which further implies that this string is not of this format. X, y squared z does not belong to the language L prime, which further implies language L prime is not regular, which further implies, due to the previous discussion that we had regarding the closure properties of the regular languages, which further implies L, the original language L, is also non-regular. Okay, so this whole discussion, we use this whole discussion to show that this original language L is not regular. Just to summarize, we started to prove that this language is not regular. We tried to use the pumping lemma to do that, but we haven't been able to do that directly using on this language. We concluded that that doesn't mean L is regular. We tried further by considering a related language, basically some language that is very similar to its complement. It's just the complement of L, but we need to introduce this 0 star, 1 star so that they will be in this format. Finally, with this construction, we can see that proving L prime's non-regularity is also the same as proving L's non-regularity, okay, due to this construction in here, which implies that if we just prove the non-regularity of L prime, it also means that L is non-regular. And that's what we did in this part. We proved that L prime is non-regular using our classical pumping lemma, and then at the end we arrive at the fact that the original language L that we were working on is non-regular.